welcome. Glad that you could be online with us here and present. I've known Sunil for about 5 or 6 years now. Great guy, very knowledgeable and very engaging and very articulate. So you'll enjoy hearing his presentation. He worked for Ericsson for many years, and now he's at AT&T. And so he's going to tell us about the use cases that 5G is going to be able to enable. So Sunil, it's yours.
Thanks, Ed. Thanks for the opportunity. Happy to be here. Good morning, everyone. Yes, Sunil Thadani. I've been in IoT for about 10 years now, doing different roles with different companies. Currently with AT&T, working on doing business development for 5G and IoT. Thanks for being here today, and thanks, Ed, and the rest of the organizers for the opportunity here. So topic today is 5G and IoT. There are, a lot of different elements of 5G that kind of intersect with IoT. Different elements of 5G enable different types of use cases in IoT. What we're going to focus in this session today are two specific elements of 5G architecture and some interesting use cases that they enable in IoT. And this also happens to be aligned with AT&T's 5G rollout strategy. In the sense, this is where the initial focus is for AT&T in 5G rollout, primarily focusing on enterprise and IoT, not primarily, I should say exclusively focusing on enterprise and IoT. So the initial rollout of 5G that AT&T has been doing for the last almost 2 years now, 18 to 24 months, it has been exclusively for enterprises and focused on IoT use cases. So it's not, initial rollout is not targeted at consumers trying to download 8K high def video on your mobile device. That's not the focus initially. It's exclusively for enterprises and exclusively for IoT use cases. So kind of aligns with that strategy as well. So the flow of the presentation is, I'll start with a use case that sets the stage, highlights the challenges that need to be addressed for those specific types of use cases. It'll also give you a flavor for the types of use cases we are interested in, we're focusing on in this session here. And then I'll talk a little bit about the specific elements of the 5G architecture that we are focusing on here that enable these use cases. As I mentioned, 5G has a lot of different building blocks, a lot of different pieces, and different building blocks kind of enable different capabilities or bring in different benefits, different value to the network and to the overall solution. So we'll focus on two elements, on the radio access part and on edge compute, and what are the benefits of those and how they enable certain types of use cases. And finally, we'll kind of close the loop by coming back to the use cases and how these use cases leverage these capabilities of 5G to deliver the value. So that's going to be the flow of the presentation. Let me start with the use case here. So the use case here is of automated guided vehicle. I want to highlight this is not autonomous guided vehicle, it's automated guided vehicle. So these are vehicles that move around on factory floors, for example, or in a warehouse, moving stuff around, materials around. So it could be taking materials from receiving to different locations on the factory floor, picking up somewhat manufactured pieces from one point to another point on the factory floor, or taking manufactured items from the factory floor to the warehouse locations. So basically moving material around on the factory floor or between the factory floor and the warehouse. That's the primary role for these AGVs. And these AGVs are pretty, I would say, dumb in the sense they don't have any onboard smarts at all. Very basic capabilities in terms of obstacle avoidance, but other than that, they don't do a lot. They are controlled completely by a central control unit. So all these vehicles moving around on the factory floor, they're all are in constant touch with a centralized control unit, which is kind of giving them instructions in real time. And as you can imagine, it's a fairly dynamic environment. So imagine one of these vehicles starts from point A, is taking some materials from point A to point B on the factory floor. And as it is going, it might get instructions halfway through. Oh, by the way, you're heading towards B. There are some additional things that need to go in the direction. Pick it up from this point C and deliver it to B, or deliver it to another point close to B, right? So you need to have this constant communication with the control unit, central control unit. So that's the environment in which these AGVs are operating. And the challenge for these guys was these AGVs are moving around, so it's all wireless communication, as you can imagine, right? And oftentimes, in most places today in the factories, people tend to rely on Wi-Fi. I guess that's the common, wireless transport that's used. It has limitations in an environment like this, where there's a large amounts of data that need to be communicated back and forth over the wireless connection, with lots and lots of devices on the factory floor, not just these vehicles, but there are lots of other devices that are communicating and sending data over the network. So what happens is, first of all, the Wi-Fi getting coverage, wireless coverage, uniform wireless coverage over a very large area. Some of these factories, warehouses are, maybe a couple of football fields, very large, right? Imagine a refinery environment, even larger campus, right? So getting consistent wireless coverage across that entire area is a big challenge. So what happens is, as these vehicles moving around, they get into spots where the coverage may not be the best, or coverage is not bad, but there are a lot of devices competing for that limited spectrum, limited transport, and can result in latency issues. And the way these AGVs are designed is if it loses contact with the control unit, it slows down or just stops. That's how they're designed to operate. So what was happening was, these AGVs were operating at a much lower efficiency than they could have if these issues were not there. So because of communication with the control unit is not the best, it's waiting for data to come back from there, or so latency issues that was causing these AGVs to slow down, and in a lot of cases just halt. So obviously that impacts the operating efficiency here. So that was a challenge that that needs to be addressed, and you can extend this scenario to other use cases, like pretty much anything that involve large amount of data. Like, for example, you might have video as a sensor on the factory floor, which is becoming increasingly common these days. Video as a sensor, for example, multiple cameras along the production line monitoring the flow of things on the production line to detect any anomalies. And based on that, somebody needs to take some corrective action, right? So stuff is moving on the production line. There are cameras along the production line that are constantly monitoring what is moving in the production line, looking for anomalies, quality issues, things not as expected. So basically looking for any sort of anomalies on the production line. So imagine this live video going from multiple cameras to a control unit where the analytics happens, and then taking corrective action in real time. Latency is of is quite important here. So these are the kind of use cases where you're relying on efficient, very fast wireless communication with really, really low latency. And when we're talking low latency here, we're talking order of milliseconds, tens of milliseconds. Just to give you an idea, typical latency on a wireless network is about, to do something on your device, goes through the radio network through the central office packet core to the cloud application and back is usually a few hundred milliseconds, just to put this in perspective. You are looking for latencies of tens of milliseconds to address these kind of use cases. So that's the challenge that we're trying to address here. And we'll talk about a few things in 5G that focus on these kind of use cases. Any questions, comments here? Okay, so 5G, when you hear a lot about 5G, and there are a lot of different pieces of 5G, as I said earlier on, which enable different things, bring in different capabilities into the network. One of the things about 5G is, when we went from 2G to 3G or went from 3G to 4G, it was all about bandwidth. It was pretty much one-dimensional value that we were getting, right? I mean, just faster speed, and that was very important at that point. Going from 4G to 5G is a little more complex. It's not just about bandwidth. That's one of the benefits, or could be one of the benefits. There are actually a lot of 5G use cases where bandwidth is not even an issue. Right? So it could be bandwidth, it could be latency, it could be data control in terms of localization, different value propositions of 5G depending on what you're focusing on. And if you focus on the low end, the massive IoT use cases where you talk about NB-IoT and all that, which is now also governed by the 5G architecture, it's the really, really lowest spectrum, really low bandwidth you're talking about, right? So the point here is depending on what value you want to focus on, what capabilities you want to focus on, that will determine what aspects of 5G, what architectural elements of 5G you want to focus on as you do the transformation from your existing network to 5G. So different building blocks are obviously going from left to right on this slide. You have the devices, obviously, you have to support 5G spectrum and capabilities. Then, of course, the radio access itself, as I mentioned, varies from all the way from extremely low speed, low bandwidth like NB-IoT, all the way to millimeter wave, to in between you have the low band and mid band sub-6 5G spectrum. Then from radio access, after that is the edge compute itself, which is a very important concept in 5G architecture, and I'll talk about that as well. Finally, the transport all the way to the core, the packet core. So these are all different elements or building blocks of 5G. For the use case I just described, what we are going to focus on in this is these two elements of 5G here, the specific features of the radio network and specific features of edge compute. These are the two elements we're going to focus on in our presentation today, and see how they help us address the use case that we just talked about. Okay. So I'll start with the radio access first, and then we'll talk about the edge compute. So talking about the radio access, most of the time when we talk about 5G spectrums, you must have heard of, the two broad categories are that, get referred to talking about 5G in 5G context is the sub-6 and millimeter wave. These are the two most common categories of spectrum you hit. What you see on the right-hand side kind of demonstrates the range of these two categories of spectrum. So you see the two large circles, those are the sub-6. These circles demonstrate the extent of coverage. So you have the low band frequency and mid band frequencies, which give you pretty good coverage comparable to LTE that you have today, maybe up to a few miles, depending on, urban, suburban areas or rural areas, or, how dense the user density is, depends on that as well. So The sub-6, in terms of range, I would say is comparable. Best way to compare that is the LTE coverage. You get broad coverage, you put a cell tower, you can cover up to a few miles, depending on the terrain and the location. And then the second category is the millimeter wave that tends to be in the really, really high gigahertz range. There, the coverage is really, really small, as you can see from the size of the circle on the right-hand side. So that is more like 100 yards, few hundred yards at the most. That's the kind of coverage you get from this millimeter wave spectrum. There, the focus is on, let's say you want to deploy this on a factory floor, like the example that we just saw, in a warehouse, on a refinery campus, for example. So those are the places where you would deploy a millimeter wave radio. Very limited coverage, extremely high bandwidth, high speeds is what you're looking for, as is the note here on the slide says fiber-like speeds is what you're looking at. Right? So that's what you get. So comparing the two categories here, the mid and low bands versus the millimeter wave, sub-6 versus the millimeter wave, what you can see here is coverage-wise, on the mid and low bands on sub-6 side, you get much better coverage comparable to what you have in LTE, for example. On the millimeter wave, sometimes we refer to as 5G plus. It's like a hotspot, kind of, or you can think of, or even a better comparison for millimeter wave would be, if you're familiar with in-building solutions, like your microcells, for example, or a DAS, those are a good comparison to millimeter wave radios. So that's about the coverage. Capacity for sub-6, the capacity is a little bit better than LTE. Whereas on the millimeter wave, it's about 10 times. So for sub-6, you might have average speed of, let's say, average speed you might get around 40 megabits per second. On millimeter wave, average speeds you might get up to 400 megabits per second. Peaks you can get up to about 2 gig per second on millimeter wave. So multi-gig throughput you can get on that. Mobility-wise, sub-6 is pretty good, just like LTE. That's the primary objective of sub-6 is for mass consumption as you're moving around with your tablet, with your phone, moving from cell tower to cell tower. Mobility is seamless, just like you have come to expect in LTE. For millimeter wave, that's not the primary objective. It's not designed for that. So it is as the first, based on the coverage you would expect. The primary objective there is on very high throughput, very high bandwidth in a limited area where mobility is not the most. I mean, within the coverage of the cell tower, no problem. But when you move out, either you fall back to what we call as the sub-6 or the macro tower. That's the typical use case scenario that works, right? So you might have a millimeter wave coverage in a specific area. When you step out of that area, it falls to the main tower, the sub-6 or the macro tower for coverage. Yeah, so that's the mobility scenario that's supported there. And latency is, as you see on both the boxes, is significantly better, with caveat being with edge. I think that's the key thing. The edge compute is what helps with the latency, and we'll talk about that in a few minutes. So this is just to give you a comparison of the sub-6 and the millimeter wave. And the reason I bring this out is that the focus here in this session today is really going to be on the millimeter wave. That's what we're going to focus on. So to address the use cases we talked about here, the AGV, and then camera as a sensor, where there's a lot of video data coming from the production line to an analytics engine for real-time intervention, those are ideal cases for millimeter wave, where you have very high bandwidth requirements, very reliable connectivity you need, because otherwise it's going to, directly impact your operations. And you have a very high density of devices in that small area that are trying to connect and communicate and send data. So these are the characteristics of millimeter wave that are critical for the use cases that I just mentioned. So that's going to be the focus here on the rest of the presentation. Before I move on to the second element of the presentation on edge compute, I'll pause here. Any questions, any comments so far?
Do I just speak?
Yeah, go ahead.
Okay.
All right.
Sunil, in 3G, 4G signal strength, targeting around neg 85 to neg 75 voice data, are there similar, what's the similar 5G comparison for signal strength? Is it similar or what?
Signal strength as such, I'm not aware of the the actual values that they run into. What I would say is, when you get into millimeter wave deployments, as I said, the best comparison for millimeter wave is with what we call as in-building solutions, like you have a microcell in a building or microcell on a campus. It's like a private network in some ways. So it gives you a lot of flexibility in terms of what the signal strength needs to be. So I guess the distinction I'm trying to draw from 3G, 4G is, if you compare 3G, 4G with sub-6, they are very comparable. But when you move to millimeter wave is designed for small spaces, restricted spaces, limited spaces. There, the comparison to microcells or to in-building solution is a better comparison when you talk about the signal strength or the ability to adjust the signal strength to different levels. So, if that helps.
Thank you.
10x capacity, you're going to have 10x noise floor increase. So you could probably expect the signal strength will be on the order of 10 dB higher.
Exactly.
Hi.
Yeah, you 10 dB more, but you're not going as far, so you have to overcome less free space.
That's what I was thinking, more of a DAS comparison, right? For voice, you needed like neg 85, data, neg 75.
Mm-hmm.
How does that compare with 5G?
Yeah,
so
yeah.
that
10 times the bandwidth, you're going to have 10 times the noise, so probably not 65 in the hip.
got it. Yeah, okay. Yeah, that helps.
And I've got one too.
Go ahead, speak up.
So question about the bands that the iPhone 12 covers. I think Apple's going to make a big dent with devices and people that were holding on to older devices to update. I guess, what's the average now? 2.3 years. So there's a captive audience here. AT&T was a launch partner with the iPhone initially, but Verizon was the big launch partner for 5G. How does the banding that's supported by the iPhone 12 support AT&T's frequencies? Have you looked at the spec sheet to see how well AT&T maps to what Apple put on at a chipset level?
I am not aware of that. I mean, I've heard what you just said, but I don't know on the consumer side what the plans are. I unfortunately focus exclusively on the IoT side, and as I said, for the last almost 2 years, our initial rollout focus for 5G has been exclusively on the enterprise space. You're right. For the next version of iPhone, I guess I think Verizon has the lead there. The devices we are currently supporting or have supported for some time are Samsung devices. I think that was launched last year. S10, S20 also is compatible, of course, with AT&T network. And there are LG devices. There are a bunch of other devices. I know, I've seen the list. I don't know what the plans are with respect to Apple, unfortunately, no, on the consumer side. From the device perspective on the IoT side, the focus is we have the way it is being done is primarily what we started out with on the IoT side in 5G space was the what we call as a fixed router. Is basically Wi-Fi to millimeter wave router. That's what it is. It's a modem, 5G modem from Nighthawk. That was the first device that was launched almost 18 months back. And now there are quite a few other devices and modules that are available with very similar functionality that are being embedded into the devices themselves, like in video cameras, for example. So it support millimeter wave directly. Okay. So moving on to the edge compute part of the 5G equation in the 5G architecture. Let's see what that is. So let me, I want to go a little bit into the concept of edge, and a lot of different definitions you have come across, and different definitions, different people, depending on where they're coming from, what they're talking. Edge means different things to different people in different contexts. So let me, I just want to lay this out here to clarify exactly what we mean by edge when in the AT&T context when we're talking about it. And actually, there's some terminology I would say is maybe somewhat AT&T specific as well. So clarify that as well as we get into how this gets used into the use case. So what you see here is typical building blocks of a 4G network, wireless network, right? So you have a device, wireless device, goes through a RAN network, radio access, and then through access goes to central office, from central office to packet core, and then from packet core it gets routed to an application in the cloud somewhere. Could be public cloud or a private cloud, or could be servers on customer's premise directly, where the traffic gets routed from the packet core. Right? And what you see here on the this device is the compute for the application. Could be in a public cloud, private cloud, or could be physical hardware sitting on customer premise. So this is where your application sits. Could be, let's say, your analytics engine, for example, that's getting data from the cameras, from the video feed, and it's trying to do analytics and then response back to some sensors or sends notifications to somebody and take some actions, right? So your application is sitting here on this compute. And what this represents here, this globe here, this is the compute for the mobility network. So this is where most of the routing decisions, routing policies, DNS and translation and all of that happens. So this is call it the compute for the mobility network, right? Whatever needs to happen for the mobile network to work. Typically sits in the packet core for the most part. That's where all the translation and IP mapping and all of that happens, right? So this is a standard for a typical cellular network in 3G, 4G. This, for the most part, that's what it looks like, right? And what this gets you, as I said a few minutes back, the latency in a setup like this is usually a few hundred milliseconds, right? You do a click or take some action, the round trip all the way to the cloud app, through all these network elements to the cloud application and back, usually a few hundred milliseconds. All right. So now let's move to second view of this network, where you have the same network element here. Starting with the device, consumer device, and the radio access is still the same. So this macro network, let's say it could be a sub-6 or 5G network radio, for example. And then from let me use it. So the device connects to the radio, and then from access goes to the central office. And imagine you move this application to the central office itself, and move this mobility network compute to the central office as well. So what is happening is that some of the network functions have now moved to the central office. Not all of it, obviously. Some of it has to, there is traffic that needs to go from here all the way to the internet, will obviously still go from here to this, to the central office, to the packet core, and to the cloud, right? But imagine having some network functionality, network compute here, and application compute sitting in the central office itself. So now some of the traffic doesn't need to go all the way to the packet core, to the cloud. That compute can now happen here, what we call as a network edge, or NEC, network edge compute. So now you have this network edge compute sitting closer to where the action needs to be. And that is referred to as NEC. And with that kind of an architecture, you can get latencies of 20 to 50 milliseconds. Okay. And one more term I want to introduce here is imagine just pushing it further along the same dimension now, right? So you have a wireless device talking to the wireless network tower, let's say, for example, right? And now you have moved these two computes, the mobility network compute and the application compute, from the central office to where the cell tower is. In this case, the cell tower is, imagine the cell tower is like a micro network, like a millimeter wave radio that is sitting on customer premise, right? So in building solution, for example. So you have this little antenna, radio, call it a radio tower or a radio antenna, which is in building or on factory floor or in the warehouse, devices, wireless devices talking to that. And the mobility network function and the application compute are both sitting right next to that tower. And some of the compute can happen right there. Doesn't even need to go to the central office. With that kind of a setup, we call it, in this case, MEC, multi-access edge control. With this kind of a setup, you're talking of latencies of less than 10 milliseconds. So introducing this concept of edge in 5G is what really is really revolutionary, in the sense, completely transforms the network and makes things possible that were not possible before. And the thing that is really making this, that enables this, is the fact that this network compute that used to be or is in, like in LTE and 3G and 4G networks, it's in packet core. That's where all the network functions happen. The network policies, network routing, authentication, and what have you. All of that happens, sits in this whole mobility network compute today sits in the packet core. Traffic has to, when you turn on your device, cellular device, this traffic has to hit here for pretty much everything. That's where the HLR sits, will do the authentication of the user, will determine what services you are subscribed to, are you allowed to, what services you're allowed to access, what's your monthly usage, so forth. All of that happens here, right? So now what we have done in 5G with the introduction of VNF, virtual network functions, some of these network functions can be virtualized and can be pushed to the edge here and can be pushed to the customer edge here. So imagine some of these network functions are now actually sitting on customer premise. So if I have a MEC device on my factory floor, that MEC device actually is owned by AT&T, it belongs to AT&T, and it is hosting some of the mobility network functions that used to sit in the packet core. So virtualization of some of those functions, VNF, virtual network functions. So some of those network functions are virtualized and have been pushed down to the edge, to the central office or to the customer edge. That allows you to sit very close to where the action needs to happen, reducing latency. And that also allows me to push some of the application compute all the way to the customer edge. So now some of the compute can happen right here, and things that need to be centrally handled, they will continue to go from the cellular tower to the central office to the packet core to the cloud application. So that's the key architectural feature of 5G that enables this achieving these ultra fast speeds, really, really low latencies. And so imagine the combination of the two, the millimeter wave that gets to really high bandwidth, really robust, reliable wireless coverage in a limited area, combined with this concept of edge compute, MEC, the two together enable a whole range of use cases, very valuable use cases, which were not possible before. So moving on to, so just to demonstrate the same concept in a, I think, a slightly different diagram. I think I love this picture, kind of really lays it out clearly. So imagine what this box represents is the customer premise, what you see here in this box. So on the customer premise, you have a bunch of devices that are talking on to a micro cellular element, like a millimeter wave antenna, for example, radio, or could be even a LTE microcell here, or a DAS, for example, right? So this is talking to a cellular radio, and from here, all the control data and all the user data goes to this network element, which is sitting on customer premise. This is the virtualized network function. That's one of the things running on this piece of hardware sitting on customer premise. And then some of the mobility network functions that are residing here, obviously it will do the authentication and make sure this device is allowed to connect to this network and all that. In addition to that, it has a whole bunch of policies. And these policies determine the traffic that's coming in, this user data. Does this user data stay local? All needs to be routed to the packet core network and to the central cloud. So those policies are sitting on this MEC function and help route the traffic, split the traffic as needed. So you can have policies saying that traffic coming from these three devices has to be routed to the local network, and the rest of the cellular traffic has to go to the packet core and to the central cloud and to the internet, for example. Right? So you can have policies like that. You can have policies like all the traffic routed to this particular destination needs to be broken out to the local data center, whereas the rest of the traffic needs to go on the packet core and to the internet and wherever else to be routed. So what we have done here is by virtualizing certain...
Quick question.
You can hear me, right?
Yes.
That MEC virtual function, does that reside within the cell site?
Is it, sorry, say that again? I missed the
So
question.
where does the VNF reside is the question here.
Oh, so
Is it in the cell site or typically it used to reside called the virtual VSC initially, but I think what you're referring to here is the question is, does it reside on the cell site? Where does that VNF lie?
So I just want to qualify before I say cell site is this whole thing is on campus, let's say on the factory floor, right? So this cellular radio that you see is on the factory floor. So here when we talk about cell site, we are talking about like a microcell, for example, in-building solution. Or you have a 5G millimeter wave radio sitting on the factory floor. And right next to that is the box that hosts dysfunction. So yes, it's
totally
cell site, means it's right next to the radio that is sitting on the factory floor. But we are not talking about the macro cell tower in the traditional sense here.
Yeah. So what initially happened, because I actually worked on some of this in the past. So what happened was before you would have a BSC that was a physical unit that would networking for the various cell sites. That was virtualized. So now you have a virtualized BSC. So that became a network appliance. And then with that virtualized BSC that was managing the cell sites, then you also had a virtual networking function that helped facilitate the networking interfaces to reduce some of the latency. And actually, because it was a virtualized appliance, that could be, in theory, moved closer to the edge, because then it became not a physical piece of hardware. So as things developed and virtualization of these functions happened, it allowed flexibility with the location. So initially, a lot of this was done on OpenStack, and so those VMs were deployed, and some of the networking functions were actually controlled via OpenStack to kind of allow for that interfacing. But as it became virtualized, the point I think is making this that allowed for flexibility in location, and now that you can have co-location with your RF interfaces, whereas before you had to have it a little closer back to the packet core.
I'm familiar with it.
Exactly.
Yeah, but the VNF was also developed as well in parallel, right?
Okay. Thanks.
Does that kind of answer things? Okay.
Yep, no, absolutely, yeah, right on the mark, yeah. And then some of these, as I said, so the control data all control data is going to the packet core, for all sorts of things. But the user data, depending on the policies, can be split and kept local, or can be routed to the packet core and out to the internet or to private cloud or wherever it needs to go. Yeah. And some cases we have been doing this is some of the functions that might sit here, like, for example, you might have an analytics engine, a very common scenario, a video analytics engine, for example, that's is doing the compute, is sometimes actually co-located on the same hardware, that's hosting the VNF functions. So this is basically your cloud stack, which is VNF is one of the functions it's hosting, and in some cases we have co-located some user applications as well on that stack on the same box. Make it more efficient. So the benefits, obviously, as you can see, the biggest one, number one, is when we started out, latency was the biggest driver for this. It's kind of interesting as it is evolving, and we're doing more and more of these deployments, particularly in manufacturing. I think that's, I would say, the number one vertical where most of the action is happening with this kind of setup. We are finding out that data control seems to be equally important, not just the latency. And data control here, what I mean by that is for various reasons, pretty much all these, companies, manufacturing customers most customers are extremely sensitive to the data coming from their manufacturing facility. They are really, really, I find it paranoid, but for them, it probably business as usual. They're very particular about the data from the factory floor not leaving the factory floor. They want to keep the data local because it's highly sensitive data. So for them, that's also extremely, or I would say equally important as latency. So latency was, I would say, the initial driver, turning out data control, what data stays local on the factory floor and does not leave the factory floor versus what data can go out of the factory floor into the packet core. And maybe, to some, even to a private cloud. So that's another big enabler of that MEC has made possible, is you can now control what data stays local and stays completely private. Does not leave the factory floor. So imagine the world that we were used to, that operators on the factory floor were used to, was, the reading comes out of the machine. It is on the machine. There's a display there on the machine. You go read it, right? That reading, you note it down on a piece of paper or whatever. That reading doesn't digitally leave the factory floor ever. Right? Now, all those machines on the factory floor are connected. The data is coming to a network, and imagine they don't like the fact that all this data is actually going out somewhere. They don't feel very comfortable with that. So giving them the assurance that they have control over the data and they decide what data stays local, what data leaves the factory floor, that's apparently a big deal as well for a lot of these customers. So that's another feature: data control, latency. And then the last one, I want to touch upon that before moving back into the use cases here, is the future proofing. You see the $ there. So one is obviously the fact that now you can determine which cellular data actually leaves the factory floor. So you might be generating a live video stream from dozens of cameras on the factory floor, and none of that might be leaving the factory floor. It all stays local. So that never hits my as an AT&T's packet core, doesn't go through traverses or packet core. Guess what? It's not rated, right? So it's helps you with manage your data expenses. Obviously, you determine what actually goes to the operator's packet core network and gets rated and built. So that's one big benefit there. The other aspect of this is, once you look at this architecture, on this slide, this antenna that we have here, the wireless radio.
Spend a minute or two just talking through the business model here. Is this a private network? In this example, has this been done as a private virtual network for the customer? And so the business model really is that you're providing them with local data connectivity on some sort of flat rate, and that's basically just it, or is it? Yeah,
I think excellent question. That's where I was going. So what you see here, this cellular radio that you have here, I said that this is a millimeter wave radio for the specific use cases we're talking, right? Millimeter wave radio, obviously that is spectrum that's owned by carriers like AT&T. So AT&T owns that, and you pay for that on a monthly basis for the use of that spectrum. But that is, it's like your own private network, in the sense that radio is for your use only within this space, and you can keep all of that data local. So effectively, it has all the characteristics of a private network. Taking a step further, there is no reason this radio needs to be millimeter wave. This actually could be an LTE microcell sitting in your building, right? And all these devices could be just using LTE microcell in the building or on the factory floor, connecting to this. And all that traffic is broken down using those policies on the MEC and kept local. So you could have millimeter wave radio, you could have a LTE radio. Tomorrow, you might have a Wi-Fi sitting here right next to this for a different spectrum, different set of use cases, and that Wi-Fi traffic going through the same element here, MEC element, using the same network policies to determine and breaking out what traffic stays local, what traffic traverses to the cloud. You could have other spectrums like CBRS, for example. So talking about private networks, so if the customer wants to build a completely private network, they could get CBRS, even get prioritized CBRS spectrum, and use LTE on top of that, in which case they have their, private spectrum. MEC element, which could be from AT&T, or, you could get that from somewhere else. And then you have pretty much created your own little network on your customer premise where the spectrum, whether it is millimeter wave or CBRS or whatever else you might have, is for your own private use only. Nobody else is using that spectrum within the space, in this particular space. Only your devices are connecting to that radio. And you have complete control of what traffic you want to keep local. So if you divert all of that traffic coming into MEC to your local data center, this is your private network.
Nah.
How would the authentication work? Would I have SIMs in my IoT devices and only talk to my gateway? Would they be able to roam? How do you guys handle provisioning?
So the way that works is, so let's say if you have a millimeter wave radio here, for example, or a microcell, LT microcell, these devices will have it. So you get millimeter wave radio from AT&T, MEC from AT&T. All of these devices will have AT&T SIMs. So when it's in this building, in the range of this millimeter wave radio, they will be going through this, get authenticated here, and of course the authentication, all of that happens in the centralized packet core. Once a session is established, user data starts flowing, and that user data is subject to these policies, right? And when these devices step out of this millimeter wave range, let's say go out of the building, go out of the factory floor, they will connect to the macro, the sub-6 network or the LTE network from AT&T, and continue working there. So just like I think the best way to compare this is in-building solutions have been around for decades, right? A lot of customers have inside the building to get better coverage. They put an antenna inside the building from AT&T. When you are inside the building, all the traffic flows through that antenna. The moment you step out of the building, it goes to the macro network, to the macro tower. You don't even realize that, the handover is smooth and the billing and all that is completely transparent. Same way.
This is different, Sunil, because in the in-building solution run with AT&T, AT&T is the service provider both inside the building and outside the building.
Yes.
In this case, the discussion really is around how do I ensure and how are you handling that authentication piece around that SIM card, that device, as being uniquely operating within the factory environment. And one would question, because if it just automatically is it a roaming arrangement to the macro network so that you're really operating as a separate carrier, the factory is operating as a separate carrier, or are you really still fully in control of it as the service provider in this discussion? If you understand.
Yeah, no, really good questions here. I'm not sure if I got all of it. There was some echo, but I think some of these things you're asking are actually evolving, still evolving, to be very honest. The most common scenario, or rather the only scenario that we have been deploying for the last 18 to 24 months is where this whole setup, when I say whole setup, I mean the radio as well as the MEC is coming from AT&T. These devices have AT&T SIMs, and that's how it connects. In some cases, what we're doing is actually we are not providing the millimeter wave radio. We're using the existing in-building solution from AT&T, which then feeds to MEC and then go from there. There have been discussions on how we might interwork with in-building solution from a different carrier. So for example, you walk into a building where the in-building solution happens to be not from AT&T, let's say from Verizon, from T-Mobile or someone else, right? And the customer wants to leverage MEC in that scenario. Those scenarios haven't been sorted out yet. It's mainly all really the business discussions, not as much as a technology discussion. That really involves how an AT&T controlled MEC, AT&T owned MEC will tie into the packet core of a different carrier, right? So basically there is a network function, the network function owned by AT&T is deciding, which way the traffic routes and which traffic goes into Verizon network versus into a local network, for example. So these are obviously requires a significant amount of very new types of business agreements across carriers. I think we're quite a ways from there yet. Those conversations haven't even started. Right now, it's all the deployments that we have done, we're doing today are where the MEC and the radio are from AT&T. There are some deployments I've run into where customers are wanting to use CBRS, not owned by AT&T. They want to use CBRS, their own spectrum. And then when the subscribers roam outside, get out of the CBRS range, it roams on, AT&T. Those, I've just run into some of those use cases that are coming up. We're still trying to figure out how the rating and the business arrangement works there. So
Kay, I think you had a question, right?
Yes. Is the 5 millimeter wave building penetration still a problem, or has that been solved?
Ed, can you repeat that question, please? Again, there was a bit of an echo.
You'll repeat it.
So Kay asked if the in-building millimeter wave penetration was still problematic.
In what way? Problematic in?
Yeah, penetration. From what I heard, 5 millimeter penetration into a building is like a brick building is problematic.
You're right. Yeah.
Bird or do something to take that wave inside. Has that been solved?
No. That's I think that's really solving that would be changing the laws of physics in my view. Just the bandwidth it operates in gigahertz, high gigahertz. You're absolutely right. It does not penetrate well through obstructions. So the use cases for these are really like is using on a factory floor, for example. Very large open area, few obstructions. You put the radio slightly at an elevation so that you pretty much have a line of sight coverage to most of these places, or with some obstructions it can get. Or in a large warehouse, in a large refinery, for example. So those are the places where this works perfect. When I say in building, maybe I should be careful. When I say in building, I really meant in a limited closed space. We're not talking like a traditional office building or an apartment building where you have so many walls and barriers. This will not be a millimeter wave will not be a good solution there. In building places where they've used this is again in large labs, for example, it works really well. A very large lobby of a hospital, it works really well. So those are the kind of places with few physical obstructions, with the line of sight visibility, for the most places with few obstructions here and there, it works okay. But you're absolutely right. Doesn't work very well through walls and basements, and it's not suitable for that kind of a setup. So there, what we have done is we have used the existing in-building LTE solution, tie into the MEC, and then if you need environments where you want to use cellular and still be able to control the latency and the data privacy, you can introduce a MEC into work with the in-building LTE solution, which gives you really good coverage.
So,
would y'all be interested in visiting with someone who believes that they do have a solution for that?
Okay. You mean to improve the coverage in spaces with okay, that's
getting from outside to inside, so you don't have to do so much conversion.
All right. I think that's pretty much what I had on the deck here. Then, yeah, you can imagine how this would apply to the use case we looked at initially. Millimeter wave radio in combination with the MEC gets you really, really low latencies, less than 10 milliseconds we're talking here. It's extremely important in pretty much all video-related real-time applications where you need to react in real time to what's happening on the factory floor, or these vehicles are moving around. You need to make sure they're controlled effectively in real time. Other use cases. This is another use case where you see inventory robot in a retail store moving along the shelves, trying to determine the inventory in the shelf, right? So it's basically moving along the shelves and reading the inventory in the shelf. And it's sending all the data, a lot of data, to sell on site in the store, for example. And then majority of the data then gets routed. There is a mech sitting on premise. A lot of the data gets routed locally to determine, what the inventory is like, and the relevant people will get notified, and the rest of the data might be going back to the cloud and into the central server. This is an example. Some of the characteristics of applications use cases. I like this. This is an interesting slide that kind of some interesting data point here. Shows how the work, for the last few decades, couple of decades, there has been a trend moving the compute out to the cloud, mainly to realize operational efficiencies, right? And gain flexibilities. You don't need to keep your own hardware, don't need to maintain it. You get flexibility by moving it to the cloud and all of that stuff, right? Makes a lot of awesome business case, moving all the compute out to the cloud as much as possible. Now, as you can see, there's Gartner prediction that in the next few years, 75% of the enterprise data will be processed at the edge. The flow is happening the other way around. And it's not that the compute that was happening in the cloud is now all of that going to happen to the edge. No, that's not. I don't think that's the implication here. I think the implication here is as you introduce new IoT use cases, a lot of this operational data that is being generated, a lot of that operational data really has a value right here in real time. A sensor here sending a reading every 10 seconds of the temperature has a value only in real time. Next day, I couldn't care less what the value of the temperature was every 10 seconds yesterday, right? The only thing I want to know is the temperature right now is drifting beyond outside of certain threshold. I need to take some action right now. So a lot of that data that is being generated, operational data by these sensors, video sensors, other sensors, that has value only in immediate action, which happens at the edge. Only the summary of the data, aggregated values of the data need to be transmitted and stored in the cloud. So when it says 75% of the data will be consumed at the cloud, it will be consumed at the edge, it's referring, I think, to the operations data that is being generated, large volumes of data, operations data, that needs to be consumed at the edge to take immediate actions. And then the summary or the summarized values of that aggregated values of the data might be transferred to the central cloud for storage, for analytics, and for whatever else you want to, long-term things that you might want to do.
So there was a question from online. If 5G is deployed inside a factory building, is part of the AT&T business case evolve frequency reuse? Sorry. It's in the chat window if you can see it.
Oh, okay. Is part of the AT&T business case involve frequency? Oh, I see. Absolutely. Thanks for, makes it a lot easier. So when you say frequency reuse, so if you have a millimeter wave radio, let's say inside on the factory floor in one place, absolutely the same frequency will be used another factory, or could be even on this different part of the refinery, for example, might have another millimeter wave radio using the same frequency. Absolutely. So if that's what you mean, the answer is yes. These are not exclusive dedicated frequencies. I think, again, the best comparison here, analogy here is to the in-building solutions that we have today for LTE. So you might have an LTE radio in a building for coverage inside the building. You go to a block down, and the building will have another LTE radio inside the building, might be using the same frequency. Maybe a block down, maybe not this building next door, but a block down will use the same frequency, yes. So you're not really buying, the customer is not really buying the spectrum from AT&T, they're kind of using it in a limited space, so to speak.
Let's give Sunil a hand, guys. Thank you for doing this.
Thank you.